Yeah, from now on, we will deal with electronic transport properties in chapter 12, electronic transport. Here we will deal with electronic transport properties. In this chapter, we deal with metallic property, and first one is the Drude model. And anyway, then the electronic transport properties is important in Drude model, and secondly, the Sommerfeld model. And the Sommerfeld in our textbook, Sommerfeld model is discussed in the thermal transport properties, because the Sommerfeld model calculates the heat capacity, electron heat capacity. Therefore, and when we can go back to the electronic Sommerfeld model in heat capacity chapter. And anyway, here Drude model is a simple electronic transport, and basically, and Drude model deals with the electron as particles, and particles can scatter with imperfections like defect or grain boundary or the ions, and there are so many imperfections in solid state, and the Drude model deals with electron gas. Electron gas free to move in the solid, and the solid consists with partially positively charged ionic cores, and for example, and there are periodic ionic cores, and electrons scatter, and also in like this, and also scattering process, and the electron transport can think about that ballistic scattering with ions, what are imperfections, impurities, whether buoys, and anyway, so many imperfections in solid. And here, the assumptions of Drude model. Assumptions of Drude model is that electron gas electron can be treated as gas, particle gas, electronic particle gas, free to move between positively charged ionic cores. And the first assumption is that a collision is the scattering of an electron by an ionic core. And this case is the ion, positively charged ions, and electrons scatter with the positive ion cores. And anyway, basically, electron is minus, but ion core is a plus. Basically, plus and minus attract with each other, but there are so many ions and so many electrons and so many ions, and the interaction is very weak. We can understood in this case that actually men and women attract with each other in a single, when we consider it a single particle, and also basically instinct attracts with each other. But when we in many crowds, so many men and women, then they do not care with each other. And but it means that if there are so many many interaction between ionic cores and electrons, and they neglect these interactions, just only the scattering. And in a crowds, we do not take into account the man and woman, but only the mankind, only people can be treated at a scattering center. And that's a basic, there is a similar, there is a similar idea. And actually, electrons do not interact with each other also. And it means that electron is minus minus repel with each other for single particle interaction. But in many electrons, in solid state, electrons can be treated as single particle because so many electrons and so many ions, the interaction cancel with each other. And here, electrons do not interact with each other. Here we, in other words, we call it as a free electron approximation. Electron can be considered as a free electron because even though there are many electrons. And also, the third assumption is a relaxation time approximation. And when you think about the scattering, there is a time for the scattering tau 1, and also the scattering tau 1 and tau 2 and something like that. And we can make average value for the time I. Then the average value of the time constant of the collision, it is relaxation time. And the probability, then the probability of collision per unit time is proportional to the inverse tau. Here is the tau is the relaxation time. Relaxation time is the time constant of the scattering, average value of the scattering. And also, inverse tau is the scattering rate. Scattering rate is the probability of the collision per unit time, and it is a relaxation time approximation. And the fourth one is that electrons achieve thermal equilibrium. Electrons achieves thermal equilibrium by collisions of surroundings. It means that we only treated kinetics, not dynamics. And basically, because dynamics deals with the time-dependent behavior of time-dependent behavior, and the kinetics deals with the thermal equilibrium. And basically, the thermal equilibrium state is enough to describe the real state of the system. And also here, by using the relaxation time approximation, then we can calculate the electronic transport properties like electronic conductivity, electrical conductivity. And let's use the relaxation time approximation. And the current density of electrons can be defined by that current density minus NeV. And let's consider unit. And anyway, and here in the right side, N, the dimension, is the number per cubic centimeter, and E is the Coulomb, and V is that centimeter per second. Then is that number Coulomb, and sec square. Coulomb here, no, I'm sorry. Coulomb per sec is ampere. Yeah, therefore the dimension the dimension of the current density is the ampere per square centimeter. Square centimeter means that cross-sectional. Yeah, cross-sectional area. And the current, the electric current in a cross-sectional, in a defined cross-sectional area, it is the current density of electron. And anyway, because of the P equal to mv, and the current density can be written down minus Ne over m. Here m means the electronic mass, and P, because we treated electron as a free electron, therefore the mass is a bare electron mass. And here the increase of momentum in time by applying electric field, the electron accelerates. Therefore, the momentum difference has the force. It is a force, and dt means that this is a momentum difference. But here, actual force in a time plus dt can be think about that ft plus, in the Taylor expansion, this function, any function can be expanded like a Taylor expansion, and the first order is that df dt delta t, and there are higher order term. And only when you think about that only first order term, and then it is that order of delta t square, because and this is first order term delta t multiply or delta t also, therefore delta t square high order, and F means that it is external force like electromagnetic force. Then from the assumption, the probability of the collision is proportional to the 1 over tau. It is relaxation and collision rate. It is that we call scattering rate. Scattering rate, the probability of collision during delta t is that collision rate is 1 over tau, and in unit time, but in delta t, the probability collision should be multiplied dt, delta t. In other words, the probability of surviving without collision is that 1 minus this function, 1 minus dt over tau. And this function, this value is the probability of collision, and it is a probability of the without collision. Therefore, and this momentum change as t plus delta t can be write down delta t here because the momentum increase can only think about that think about the electrons without collision, and therefore it is a probability of without collision 1 minus dt over tau. It is a probability of non-collision. And also the real momentum difference is that the pt plus ft delta t plus order of high order delta t square, and it is acquired. It is that this term is original momentum acquired additional momentum, and therefore to solve the velocity, then the F equal to ma here, the equation of motion of electron, the scattering or collision can act as a drag force, and therefore the ma, F equal to ma dv dt, is that it is accelerated by the electric field, and also because of the collision, and we should think about the drag force. And drag force is a gv. Drag force is proportional to the velocity, and it is a linear first order differential equation, and it is a linear first order differential equation because it can be the standard form of the linear differential equation is that y prime plus pxy equal to qx. I believe that you already know how to solve the differential equation in the mathematical physics course, but I think that some of them you may forgot how to solve these linear differential equations. And anyway, in this case, we should think about that integrating factor. Then integrating factor u. Then we multiply the integrating factor in both sides. Then you can write down uy prime plus upy equal to qu. Then in the left side is that uy prime equal to qu. Here, then let's consider that the uy prime, then it is u prime y plus yu prime, and then let's surmise that it is qu. Then here, if we assume that it is u prime equal to up, then it holds above the equations. And then if the u prime equal to up, then u prime is a up, then it is the same with these equations. It holds if like this. Then here u prime equal up means that, in other words, it is the du dx equal to up, then du over u equal to p dx. Then integrating in both sides, and ln u equal to integral px dx. Then integrating factor u is that exponential integral px dx. Anyway, there is a constant c, but we only consider on the integral. We can choose the constant is 0, and also it is an integrating factor. Therefore, we can solve the equations in the above equations, and this equation of motion can be written down like this in the standard form. dv dt equal to, not equal, and standard form plus g over m v equal to q over me. It is a standard form of the linear first order differential equation. Then here it is a px is that the g over m, it is constant value, and the q is that q over me. Therefore, and the integrating factor is that u equal exponential integral px. P means that g over m dx. Now here, not dx but dt. Therefore, it is exponential g over mt. It is integrating factor. And integrating, let's multiply in both sides. And exponential g over mt dv dt plus g over m exponential g over mtv equal to q over m exponential g over mte. It is we multiply in both sides. Then the left hand side can be write down, it is a ddt exponential g over mtv, and it is left side, it is that q over me exponential g over mt. Therefore, by integrating, then exponential g over mtv is that integrating, then q over m multiply g over m e exponential g over mt, integrating in the right side. Therefore, it is plus c. Therefore, it is that q over g e exponential g over mt plus c. Therefore, the v is that v is that exponential term cancel with each other, and q over g e plus c exponential minus g over mt. Here, it is a solution of the velocity. And let's choose the initial condition. Initial condition by that the v0 equal to 0. And it started from the 0 velocity. Then at t equal to 0, 0 equal to q over ge equal to plus C. Therefore, C equal to minus Q over GE. Therefore, we substitute equation in here, and the VT can be write down as that Q over GE. It is that 1 minus exponential minus G of MT, and it is a solution. And here, the velocity means that it started from the zero velocity, and the V versus T, there is a saturation value. It saturates like this. Here, QE over G. And without a collision, without drag force, the velocity electron increases with time, but it can reaches to the velocity. It reaches to the speed of light. But in the scattering makes a drag force, and it saturates. There is a saturation value of the velocity. We can understood that it is similar to the solution. Is similar to the solution of the drag force in classical mechanics. And anyway, this momentum transfer, momentum relaxation time approximation, and also several approximation makes that a finite value of the velocity, and the finite value of the velocity of electron, it induces the electrical conductivity. And also here, let's calculate the electrical conductivity. In third case, electrical conductivity. And here is a DC conductivity. And we define that electrical resistivity is defined by that equal rho J. It is a basic Ohm's law. In Ohm's law, it means that V equal to IR, then the V equal to EL, and also J electric current density is that ampere per square centimeter, and therefore electric field. And also here E means that from the Ohm's law, and here rho J is that I over A L. Then here it is rho L over A is that resistance in I. Here it is identical with Ohm's law. From this definition, we can think about that actually electrical resistivity is a tensor value, and electrical resistivity is defined by that by applying electric field. By electric field, and there is a current. And anyway, in other words, and electrical resistivity, it is 1 over sigma. In other words, sigma is that by applying sigma, electrical conductivity is defined by applying electric field and the current density. And it is electrical conductivity. But even though it is a numerator and denominator aspect component, and the sigma is the tensor value, but in general, electron accelerates along the applying direction of electric field. That's why electrical conductivity can be think about as a scalar value, because the J direction and E direction parallel with each other. And also electrical resistivity also can be considered as a scalar value, and because E direction and J direction is identical. And here, we know that J is that minus NEV, and V is that average velocity, and therefore here V is that minus NE and J, and J means that here we know that here's V equal to, from this above equation, at finite, at the long V here, the solution of the velocity from the drag force, and this can be written down like this: as a long time the finite value of the velocity of electron reaches to this value, and therefore it reaches to the QE over G. Then here we this dimension GT over M should be unitless dimension. Therefore M over G should have the time dimension. We call it is a relaxation time, or M over G should have the time dimension. We define that it is a relaxation time here. Therefore G means that 1 over G is that M tau of M. Therefore V is that minus QE tau. And here in the steady state we call that and drift velocity. Drift velocity is that here not Q but E, because Q is that minus E in electron, and Q tau of ME, it is the drift velocity. Because then J is that NQV, and V is that also NQ squared tau over M E, and in electrons NE squared tau over ME, we call it as sigma E from the Ohm's law, and therefore the electrical conductivity is that NE squared tau over M, it is 1 over rho. Then it is the definition, it is the electrical conductivity and electrical resistivity. Then also, and this it is electron kinetics by applying electric field, and the electric field parallels to the electric field and current direction parallel with each other. How about when we apply the magnetic field? Then in this case we can think about the Hall effect and magnetoresistance. Hall means the name of physicist, and Edwin Hall, who was graduate students in Johns Hopkins University, and here Edwin Hall found that it is metallic materials, and by applying electric field in this direction, and let's consider then the current direction is also x direction, but we here we Edwin Hall applied the magnetic field also in a simultaneously. Magnetic field direction is the g direction. Then from the Lorentz force, electron deflected here in this direction. Therefore, accumulated electron in this side. Then, because of the accumulation of electron in the opposite side, there is mirror electrons, mirror images, mirror charge is there is a mirror charge in the opposite side, and because of the plus and minus electronic configuration, and in the inside, and the electric field along the y direction is generated, and it causes by the Lorentz force of the electron accumulation by applying magnetic field. And in this case, the whole effect is occurred that the electric field direction and the magnetic field direction is diagonal, not in the sample in the g direction. Electric field is the x direction, and the magnetic field should be g direction. Here is the Lorentz force. Lorentz force can be written down in a CGS unit, E of C, V cross H. Then it deflects electrons in the negative y direction. It deflects electrons in minus y direction, and it induces the positive charges, image charges generated in the opposite side, and also in equilibrium. Therefore, in equilibrium, EY, electric field along the y direction will balance with the Lorentz force, FL, Lorentz force. And here, the Lorentz force is y direction, and the Lorentz force y direction competes with the electric field for the y direction. Here, in this case, we can define that the magnetic resistance is because when you do not take into account the magnetic field, there is no electron deflection, and all the electrons participate to the conduction of electron in the direction of electric field. But when you apply magnetic field along the C direction, along the G direction, then because of the electron deflection and the number of electrons through the electric field, applying electric field direction, and decreases. Therefore, there may have the differences between the current density along the x direction. Therefore, here, then in the magnetic resistance can be defined by that. In magnetic resistance also resistance. Therefore, it defined that EX over JX. But the different thing is that the total number of electrons decreases along the x direction. Therefore, by applying magnetic field, electrical resistivity decreases or increases anyway, and it depends on the sample. And the rho 0 over rho 0, it is defined that it is a magnetic resistance. And also, another definition. There is another definition, and the Lorentz force acting on electrons. Here we define that the Hall coefficient And Lorentz for generalized Lorentz force is that minus E plus 1 of C V cross H is a general form of the Lorentz force. And also then the time derivative with the momentum is that minus E plus 1 over MC P cross H. Anyway, we think about drag force. And here, then we should calculate this term. P cross H is that IJK and PX, PY, PG, and the magnetic field direction is the G direction. Therefore, I direction HPY minus J direction PXH. Okay. Therefore, the X in the steady state, there is no external force. Therefore, in the X component is 0, minus EX, and minus, let's call that here this one EH over MC, we define that EH over MC, we define it is cyclotron frequency, because it is that it related with oscillation. It is a cyclotron frequency. Anyway, it is omega C Py minus Px over tau. It is X component. And the Y component is that minus EY minus omega plus omega C minus plus Px minus Py over tau. It is a steady state. And also here, because the electrical conductivity, the definition is that Ne square tau over m, and the Ji is minus Ne over m Pi. Then Ne, because here let's multiply Ne tau over m in this case, in this side, multiply in both sides Ne tau over m, and also this term, let's move this one, then it is this term here becomes electrical conductivity. Therefore, sigma 0 Ex equal to omega multiplying minus, then omega C tau. Here P is that mj over Ne, here tau jy plus jx, and here in the y direction, sigma 0 Ey equal to minus omega C tau jx plus jy. And the whole Hall effect, Hall field, we define the Hall field by the y direction electric field is that minus omega c tau over sigma 0 Jx at the steady state at Jy equal to 0 at steady state. In steady state, it is a thermal equilibrium state and there is no y current direction. Therefore, it is in steady state, Ey can be written down like this. In other words, and tau and omega c, when we multiply from the tau and omega c, in other words, it is h over nec Jx. Because omega c is omega c here in the tau okay. Then therefore the Hall coefficients is defined that Hall coefficient is defined that Ey versus Ey over Jxh. Then it is minus 1 over nec in CGS. In NKS, minus 1 over ne. Therefore, it is important we use many times in experiments in the Hall effect and the Hall coefficient. By calculating the Hall coefficients, we can obtain the carrier concentration because E is elementary charge and c is the velocity of speed of light, and therefore, and by measuring the Hall coefficient, and we can calculate the Hall carrier concentration. Then how to calculate the Hall coefficients? Then when we measure the Hall measurement is like this, and also this configuration is a sample. It is current direction I plus I minus. Then in the off diagonal components V plus V minus, and here we measure the voltage difference. It is a voltage difference. Then the rho x y direction we can calculate, and also we can measure the rho x y direction and the current. It is a v x y v y direction. R x y means that the Vy over Ix. It is then rho xy is that Rxy. Rxy is that the Hall resistance and multiply d. Here is the d, the thickness of sample. Then Hall coefficients can be calculated rho xy over h, because Ey of Jx is the rho xy, and we can calculate the Hall coefficient. Then it is identical minus 1 over nec. Therefore, by measuring the Hall coefficients, Hall coefficient and Hall resistivity, we measure the Hall resistivity, and the Hall resistivity divided by the magnetic field is the Hall coefficient, and the Hall coefficient can be, from using the Hall coefficient, can calculate the Hall carrier density. It is important in the experiment.